Hi, welcome back to my lecture. So, we will continue with induction motors, performance and operation. Just recapitulating, we have already done how the induction motor is constructed, how the rotating magnetic field is created and there is a rotor. So, these rotors are responsible for induced currents and induced currents interacting with the rotating magnetic field, we get a torque. So, these are the concepts now how we will analyze the induction motor. We will get into the performance in steady state. So, we will discuss about the how to develop the equivalent circuit, torque speed characteristics, efficiency. Okay. So, you see you have these are the motor pictures you saw. Today I have got a laboratory motor. So, I will show you that laboratory motor. So, here actually we have opened it up, you can see. So, this is the motor you can see here. This is the stator of the motor, this is the windings. So, these are the terminals as you can see. These are terminals which are coming out. You can see 3-phase terminals. This is a star connected motor. So, you can see this is the name plate of the motor. If I can zoom, somebody can zoom it a little bit. So, this is the name plate of the motor. So, every motor has a name plate. So, what it is written, I will just read it out. It returns the phase, how the phase sequence, how much amperes, volts, RPM, etc. rating. So, it is not visible clearly because it is a old motor. So, this is the rating, RPM is 1440 RPM, supply is 220 volts, 6 ampere, it is a 2 HP motor, 2 HP and it is written continuous rating. See, that is how it is written. So, number of phases is 3 phase 220 volt motor. So, this is the name plate. So, this shows and rating is continuous. Continuous means whenever it operates continuously, this motor will have a temperature rise which will not be harmful. And you can see this is called the cage rotor. As you can see here, I am showing here. So, this is the cage rotor. So, you can see this is this is a short circuited cage winding. So, both the side, this is squirrel cage rotor. So, it is having the bearing. So, it will be fitted in the motor this way. Okay. So, this is all about the motor. So, let us go into the details here. So, these are, so let us get into the details, we will come back to this later on if necessary. So, these are the stators as you see here and the rotor you saw here. I have shown you a practical motor with a name plate. So, we have to build the equivalent circuit of this motor. So, here we started from flux and MMF concepts. The stator is a very balanced winding. You see this balanced winding. This is the balanced 3-phase winding. I will use the laser to show you. So, this is a balanced winding. You see balanced winding. So, the rotor is balanced because it is a round rotor. So, balanced 3-phase winding. So, MMF concept translates steady state equivalent. So, we can convert this whole thing into a steady state equivalent circuit just like transformer because of its symmetry and balance. So, it is not so easy to analyze the unbalance, but when it is a balanced supply, we can easily make lot of approximations which will work. So, the per phase modeling concept, that means the line currents which are flowing equal to phase currents, line to neutral voltage are used. So, this phase voltage, so it is like a star, the phase voltage is used and every phase is 120 degree apart and the winding also, the winding axis is 120 degree apart. So, you should know the winding, what is the axis of a winding you can see. So, if there is a coil like this, the coil, the coil is like this. So, you can see the coil. So, the coil, if the coil is wound like this is the coil, this is in one slot, this is one side of the coil, this is another side of coil. If the coil is wound like this, so this you ignore, this one I am not going to erase it, I don't know how to erase. Okay. Now it is erasable. So, if you erase this, I will draw it again. Okay, so this is coil, this is in one slot. So this slot current goes in and this slot is exactly 180 degree electrical apart. So this will create a flux. So this flux will go into it. So this is called, this is for coil. So so this is called one coil. So there will be several coils. So the coil axis is here. This is called coil axis. Coil axis, which is the flux is, the current is going like this. So like this. So flux will be, so according to Ampere's law, it will be inside. So dot, flux will be like dot. So this is on the stator. So flux will enter into the rotor. So this is the coil axis. So each coil axis is displaced by phase A, phase B, phase C are displaced by 120 degree. So if you, I also discussed this figure has been taken from M.G. Say, it's a very famous book, old book. So this is the rotor, this is the stator, we discussed about it last time, right. Whenever there is a slip is equal to 1, that means in the starting, this is like a transformer, that means the rotor is not rotating, only the stator magnetic field is rotating, it is cutting the rotor turns, it is cutting the rotor turns. So this rotor turns induce voltage and as a result there is current. So there is 3-phase balanced current. If the stator is having balanced 3-phase supply and it is rotating, a constant magnetic field is rotating, so it will cut the magnetic field of the conductors of the rotor, and a balanced 3-phase current will be also created there. The rotor is reached, it is automatic, it is a law of the nature, and they will try to oppose the very cause. So therefore this balanced 3-phase stator and balanced 3-phase rotor, they can be brought down to just single phase. So when slip is equal to 1, the voltage induced in this is equal to E2, which is basically the stator and rotor turns ratio, and there are some other rotational components, which is a constant. That means at slip is equal to 1, E1 by E2 is a constant K. So this cannot change. This depends upon the construction of the motor construction. Okay, that includes the slip supply frequency also and supply frequency. You can say that how fast it is rotating, synchronous speed. So you can say that when slip is decreasing, because when the speed, this is omega r is equal to 0. When omega r increases, as you have seen, slip reduces. Slip will become less and less. So slip will reduce. So when slip is reducing, so this voltage will reduce. So rotor has a circuit per phase. This is all per phase, per single phase, because all balanced. Because of balanced, we can do per phase. So you can say the rotor circuit is this. So in this rotor circuit, the frequency is different from stator. But if you do little manipulations, you can divide S everywhere, the rotor circuit becomes this. Here, as I have told last time, that this is at slip frequency, but this is at supply frequency. Just by dividing S, you can assume. So every calculation will remain same. So again, from this I have derived this. I have separated this rotor resistance and a component of the resistance which appears here. So this is responsible for torque, mechanical power and torque. So this is what we have discussed. And if you consider the corresponding phasor diagram, this is the supply voltage. Considering no drop, this is the terminal voltage, which is equal to supply voltage of the motor, and there is a magnetizing current which will flow, we will see, which will be 90 degree to each, and there will be a current because of rotor I2, which will be reflected in the stator, and the voltage induces SE2 here in the stator, and I1 is here. So you can say that, the voltage I1, the current I2 is reflected in I1. So the I1 plus this IM magnetizing current will become the total rotor current, stator current, supply current. We will see just like transformers. So moving forward, this we have discussed. So the goal is to translate the air gap flux. Remember, the flux which is passing here is the air gap flux, mutual flux you can say, which is going from the stator. There will be some leakage which will not go to stator, there will be leakage, but there will be some flux which will be linking the rotor. So this air gap flux we call it, and MMA behavior into electrical equivalent circuit. So you don't have to get into flux details, we can because of the balanced nature, we can get the whole thing into the stator reference frame, and we can get rid of these flux calculations. We can just do calculations using the current. So, the assumption is this, we have already said 120 degree apart, line current is equal to phase current and line to neutral voltage is used. So, this is the equivalent circuit only for the stator. We have discussed this earlier, but once again I am coming. Forget about the rotor case side. Stator has a resistance, stator resistance. Stator has a leakage inductance, because stator winding, some flux will, this is the common flux which will go to the rotor, but this flux will only stay in the stator. So, this is called leakage inductance. Leakage, just like transformer, leakage inductance. That means, some flux in the stator here, in the stator will be here, it will not link to the rotor, but some will link to the rotor. So, these are all leakage path. So, this leakage is taken care of by leakage inductance, you can see here, and there is a stator resistance, then there is a mutual. This mutual means whatever mutual flux. So, there are two fluxes, phi mutual and phi leakage. So, voltage is induced because of this, and this voltage is neglecting the resistive drop is equal to V1. Okay. So, therefore, this is mutual flux d lambda m, right, by dt, because n is there also. So, this is lambda m, which is because of mutual flux, is equal to the voltage induced here. This is the voltage induced here. This is E1. So, same voltage is also induced proportional to this is induced in the stator. If you, because depending upon the turns ratio of the rotor and stator, the voltage induced in the rotor also proportional to this multiplied by the slip. So, you can say that at the starting, this E1, E2 when it is transferred to the primary, just like transformer, they can be here. This is E1, this is equal to E2. So, this is the resistive drop and leakage drop, and finally it becomes V1, just like transformer. So, let us get into stator voltage equation. What will be the stator voltage equation? So, there is a current flowing here. This current is due to two components. One is the magnetizing current, which is called I phi. This is again divided into magnetizing current into two components. One is the core loss component and magnetizing branch. This is true because stator will have is a magnetic core. You can see, just focus on this, I will show you. You can see, this is stator here. So, these are, if you look at the stator, this is the, you can see here. So, this is the, you can see here, this is the core, iron core. So, you see the flux passes through this, some flux will be leaking here, and there will be leakage. Also, there will be core loss here because of the stator stampings. There will be, this is the iron, there will be core loss. So, there will be two components here. Coming back to the slides, there will be two components here. So, one component will be because of the eddy current loss in the stator core, and one is the magnetizing component. Also, the rotor eddy current can be reflected here without loss of any this problem. So, this also reflects a part of the rotor eddy current loss, though it is not very accurate, but it is for all practical purposes. Rotor eddy current loss is also mentioned here. So, this is also because of the mutual flux which is going to the stator and rotor. So, the iron is there. So, because of iron, so there will be rotor eddy current loss. So, this is rotor plus stator eddy current loss, and there is a magnetic branch. So, this is a power component, this is the flux producing component, 90 degree to each other. So, this is the current. So, another current is reflected because of the rotor. Rotor is like a transformer, as I said. So, it gets reflected. So, the total current is I2 plus I phi, and the voltage is equal to this E2. This is the voltage induced here, plus I1 R1 plus JX1. So, V1 is the terminal voltage, E2 is the counter EMF due to air gap flux, and stator resistance, stator leakage reactance. It is same form as primary of a transformer. Just imagine that one. So, induction motor analysis is easy. Once you understand the equivalent circuit, there is nothing. It is very easy. So, if you come back to stator current decomposition, stator current will have two components, as I said, I2 plus I phi. I2 is the rotor current reflected in stator. Rotor current reflected in stator, just like transformer. In a transformer, what happened? Whenever there is a secondary current, there is a reflection in the stator. So, this total current I1 is equal to I2 plus I5 and the voltage you saw. So, this is the load component, that means this is because of the rotor component, because the more is the load, it will reflect in the stator as a load component, and I5 is the exciting current, that means I2 is equal to 0, I5 will be always there. That means in no load, when I2 is 0, when I2 is 0, no load means, remember, no load means the slip is equal to 0, there is no torque. So, when the slip becomes very small, that means as the rotor is catching up with the stator magnetic field, there is no slip. So, it is called no load, and full load means somewhere you are load externally and starting. So, during no load condition I2 is equal to 0, so this exciting current will come. So, here you have got two components IC and IM, I just discussed. IC is the core loss component, IM is the magnetizing component. So, this magnetizing branch is represented by the core loss resistance and the magnetizing impedance. So, these parameters are all evaluated at rated frequency, that means the frequency at which the motor is supposed to run. So, you can say that at rated frequency what will happen? So, there will be some drop here. So, that drop is so negligible, you can, for all practical purposes, you can say E2 is small. So, this is just identical to transformer magnetizing branch. So, going further, so this again rotor is represented as you say, rotor circuit is I2 by E2, that is the impedance of rotor circuit. This is the current I2, so E2 by I2. So, E2 cap you can say referred to the primary. So, rotor is short circuited, as I said, you have seen the rotor which is short circuited. This is just a metallic thing, it is shorted. So, it represented like transformer. So, you can see here the rotor is short circuited here. The rotor here you can see, this is the rotor, you can see here, this is the rotor which is short circuited. There is no winding, but the aluminum just casting. The end rings, these are called end rings, this side called end rings. These projections are because of creating fanning effect, so that there is cooling. So, this is how the rotor is constructed. So, it creates automatically 3-phase currents. Okay. So, you can see that here in the circuit. So, this rotor current is equal to this, and the referred impedance, that means there is a effective turns ratio. What is the effective turns ratio? The stator number of turns and the rotor number of turns. When slip is equal to 1, that means there is absolute standstill of the rotor during starting, or you hold the rotor and make the stator to function. So, U1 by E2, that ratio is equal to the effective number of turns, that is decided by the frequency and the number of stator and rotor turns. So, this is how you get effective number of turns. So, that is equal to, so you can refer this rotor impedance you can see here to stator by just multiplying the square of turns ratio, just like transformer. So, effective stator to rotor turns ratio, it is called effective stator to rotor turns ratio. So, this comes here. So, enables modeling squirrel cage motor, so you can just model it. So, if you go into the equivalent stationary, why do you do it? So, if you do it, you can both analyze wound rotor and squirrel cage. This is a squirrel cage motor, and you can easily do slip frequency analysis, and you can do at any frequency. We do not have to actually analyze two different frequencies. You can transfer the rotor into the stator. So, rotor frequency is different, true, but rotor frequency along with the rotor rotation, that represents equivalent to the stator magnetic field. You know, always the stator magnetic field is always in the opposition of the rotor magnetic field, they get locked, that is why it is rotating. So, rotor magnetic field is because of two things, rotation of the rotor as well as the frequency component which is created in the rotor, both together they lock. So, that is why we transfer everything to the stator frequency. So, if you look at the slip frequency rotor impedance, you can see this you have already discussed, that means this is at slip frequency. The impedance is x2 when slip is 1, at any impedance this. So, if you divide this, you know, so if you can see this expression S by this R2, so here you can see S E2 by R2 plus J x2 into S. So, this S is divided, that is why you will get E2 by R2 by S plus J x2. So, this expression is though equal to this, but the frequency of both of them are different physically. So, that is what you see, this is the exact thing, but you will see the frequency of rotor frequency S into Fe, R is the rotor frequency. So, you can see this is the rotor frequency which is equal to S into the electrical supply frequency because of the slip. So, what we do is rotor current we try to relationship like I2s is equal to I2, that is I2 refer to secondary, and this is referring is also at the frequency of the supply. So, what happened? So, E2s is equal to S into E2, and in the phasor form there is a phasor, it becomes S into E2 cap. So, it is called phasor. When there is a cap, we call it phasor. Phasor means it is a complex quantity. We have already done this complex quantity phasor diagrams, you please refer to that. So, you can see this. So, as I have said, instead of SE2, I divided SE2 cap by R2 JX2, then I JX2 into S. So, I divided S everywhere. So, this is equivalent to E2 cap by R2 plus Jx2, R2 by S. So, that is what I have done. So, R2 by S here, X2 here, E2 cap here. So, this is the this is the complete equivalent circuit. In steady state, refer to the stator with very minimal approximation, right. So, this is the exact equivalent circuit, you can say exact equivalent circuit. This is the exact equivalent circuit, all right. So, we have to use this equivalent circuit, this is per phase. So, you can compute power, what is the power, whatever power goes in, there is some loss here, there is some loss here, there is some loss here, let me do the pointer, let me use the pointer. So, there is one loss here, another loss here, there is one loss which is because of resistance, then rest of them is going as mechanical power. So, derivation of rotary impedance, so you can derive rotary impedance, that is E2, this by this already told. So, this is what is the final rotary impedance, this is the rotary impedance expression we have already done. So, this is the first, second, third S. So, S is divided in both. So, finally, you get this. This is the final rotary impedance which is referred to stator. This is referred to stator. This is referred to stator, and this frequency is at slip frequency, this is at the supply frequency. Remember, this is a very tricky thing. All the computation of power, current, magnitude will all remain same, no change. Only the frequency is different. So, two frequency components cannot be analyzed by same phasor. That is why we do the transformation by dividing this S. If you divide by S, so this becomes the same thing, alright. The magnitude all everything will remain same. So, final single phase equivalent circuit as I have shown here, this is the final circuit. Okay. Resistance is R2 by S, reactance is X2, interpretation R2 by S is having two components, one represents the rotor copper loss, that is I2 square into R2, and then whatever the total is this, So, if you subtract I2 square R2, that gives you what? The mechanical power. So, this is the rotor copper loss. This is the P mechanical, final mechanical power output. So, this is the total power input, this is called air gap power sometimes. This power goes from stator to the rotor. So, we have to analyze this, what exactly you will get, that means you will get two things, one is the torque, another is power, then from that we can find out the losses and efficiency. So, whole idea of doing this motor is, one is you have to find out the efficiency, that is very important, then torque and power. These are three things which are very important in motor. Then current, power factor, their secondary things are power factor, current. So, these are again also important things. So, efficiency decides the power loss and heat, torque decides how much load you can drive, power decides how much power you want to demand, power factor defines how much is the reactive power demand, current defines what is the rating. Here you can see the current rating is, what I can see here is 6 amperes. I can switch on the mobile torch, I can give you better because it is going on. So, I can give you a better idea. So, you can see here it is 8 amperes, 2 HP motor, 3 phase 220 volt AC. So, there is a number, so ampere is 8 amperes, 220 volt AC, 1440 RPM, it is 50 hours obviously, it can also run in 60 hours. So, rating is continuous. So, these are the things which are actually there. So, I can just rotate it little bit. Can you focus on the nameplate? It will be better. You can just focus it as much as possible, more focus. So, I can, this is the nameplate here. I don't know whether you can see it, but this is the nameplate. Anyhow, so I will show you a nameplate next time. So, you can come down. So, now you can see the air gap power is how much? Air gap power is equal to Q means number of phases. So, there are 3. In this case, Q is equal to 3. It is a 3 phase motor. Sometimes we can have 6 phase motor also. So, this is the total air gap power. In each, this is the power which is going to the rotor circuit. This consists of 2 parts. One is rotor copper loss and mechanical loss. This is a rotor copper loss, Cu loss. Copper means loss in the conductor, and rotor mechanical power developed, mechanical power. This mechanical power goes to the bearing. So, there may be friction loss also. After that, the whole thing comes to the shaft. Shaft means it is driving a load. So, this whole thing comes to the shaft. Like you have seen the drag line. Drag line you have seen in the first lecture, you saw the video. So, the boom barrier, how it goes. So, that is a load. It needs a torque and power. Alright, so this is called air gap power. Whatever power goes into rotor from the stator, it is called air gap power. So, rotor copper loss is also you have seen the rotor copper loss, Q is equal to 3 here. I am putting Q because it can be generic. So, this is called rotor copper loss, depends upon only the resistance. Okay. It is independent of slip. Remember, rotor copper loss is independent of slip. It only depends upon the magnitude of the rotor current, and I2 square means magnitude of I2 square and the rotor resistance. This is rotor resistance. You will see why the rotor resistance is important. We can increase or decrease to change the torque speed characteristic. You will see that. So, now if you go to the mechanical power developed, it is the gap power minus the rotor copper loss. So, this is 3 again here. So, this comes out to be, if you just subtract this whole power, this power 3 into minus I square R2, 3 I square R2. So, this becomes this I square R2. So, this is called the mechanical power, which is dependent upon slip. It is dependent on a function of slip. If slip is equal to 0, the mechanical power is equal to 3 I square R2. That means everything is loss. There is no mechanical power will be how much? Slip is equal to 1. 1 means the mechanical power developed is 0. Because slip 1 minus 1 is equal to 0, alright. So, you can say that, so a mechanical power is equal to 0. So, we will see that I2 also depends upon slip. So, this is a very complex function, you will see. So, how the mechanical power varies, there you have a plot. So, you cannot say whether slip is 0, it will become no, I2 also will reduce. So, both together. But when slip becomes 1, there will be finite value of I2, mechanical power developed. Slip 1 means during the first, when the motor is steady state. There is no rotation, but there will be torque. So, torque into speed is power, torque into speed is 0 initially. So, mechanical power is equal to 0. So, this is what we have known, that is rotor resistance has 2 parts, one is the loss component, one is the mechanical power component. So, this is mechanical power component is R2 into 1 minus S, R2 into 1 minus S by S. This is the mechanical power, and loss component is just R2. Alright. So, both if you add, so that becomes R2 by S. This is the total air gap power. So, slip power relationship, you know, mechanical power is equal to 1 minus S into gap power. You can see here, our gap power is 3 I square R2 by S, and if you multiply 1 minus S. So, gap power whatever goes, when the slip is less, the mechanical power is becomes equal to mechanical power gap. That means slip reduce slip, and when the slip is G1, the gap power passing to the mechanical power is 0, and rotor power is S into rotor loss. This is loss because of the rotor, S into gap. So, this is fraction, 1 minus is fraction of mechanical power, S is the rotor copper loss. So, I am going very slow. So, rotor copper loss is, you can connect to upper rotor loss slip into 1 minus S. So, higher the slip, higher is the rotor loss. Explain poor efficiency at starting. Plugging means, you know, you reverse the phase sequence. When the motor is rotating in one direction, you reverse the phase sequence. That means the magnetic field rotates in the opposite direction. So, that means Ns minus Nr becomes Ns plus Nr, because rotor is in opposite direction. So, the slip becomes more than 1. When the slip becomes more than 1, that means it comes to this side. Slip becomes more than 1, that means speed becomes negative. So, it comes to this side. So, that means this is the torque speed characteristic, you can see. So, this is the torque speed characteristic. So, when it is this slip is becoming 1 here, then it goes to 0. So, more than 1 means this way. So, it will go like this. Here in this region what will happen? In this region the speed is opposite and torque is positive. So, there will be braking. So, this is called braking region. We will see. Braking means the magnetic field is rotating in the opposite direction to the rotor. Why? Because you change the phase sequence. It was ABC, motor was rotating. Suddenly from ABC phase sequence to you made ACB. So, the magnetic field was rotating in one direction and the motor was rotating in the same direction. Now, magnetic field rotates in the other direction, motor direction opposite direction. So, this is NR, this is NS. So, in one case if NS is the thing, so here it is NS minus NR by NS is the slip. In this case, this is NS plus NR by NS, because if you consider NS, NR is opposite. So, NS minus of minus NR, so here the slip is greater than 1. So, what happens? So, there will be plugging. Plugging means they will oppose each other, torque will drive, it will try to brake. So, this is called braking region. So, that is why plugging, we call it plugging. And heavy overloads. In all these cases, when the slip is slip is more, the loss is more, because the gap power is proportional to S into rotor loss will be more. So, efficiency is poor. Therefore, rotor gets heated up, because there is copper loss, rotor gets heated up. So, whenever the motor is stalled, that means it is not moving because of some reason, it is not developing torque. So, rotor gets heated up and the winding might burn. So, that is called this happens in case of pumps. You know, in household applications there are pumps. These pumps are supposed to draw water from the wells. Sometimes in the wells there is air packet. Because of air packet, there will be lot of suction required, which needs lot of torque, which the motor cannot supply. So, motor starts, but it cannot rotate, because the torque required is so high, it cannot rotate. Once it cannot rotate, it draws more current, because of slip is equal to 1, there will be more loss means more heating, finally the winding burns out. So, therefore, there is lot of protection for this kind of thing, bimetallic relays etc., for switching off when this is high, the current is, the temperature is high. So, there are many ways to do alternate equivalent circuit. So, this is R2 is the heat, this is mechanical output. So, this you have done already. So, this is the final balance, you can see. This is the starter input power, which is 3 VI cos phi. VI cos phi is per phase. This is phase voltage, phase current. So, phase voltage, this is V phase, this is I phase. So, the total power is 3 VI cos phi, which goes as the gap power. So, this has a component of stator, copper loss, this is going to the motor. This is a total power input, you can see, input power. So, there is stator core loss. Stator core loss is PC, this is stator copper loss. After that, whatever is remaining, that goes to the air gap power, PAG. This is the air gap power. This air gap power, there is rotor copper loss, S into air gap power. This is rotor air gap, AG means air gap, is the total power. So, this after that, whatever is remaining is mechanical power. In the mechanical power, you know, this is mechanical power. This is rotor copper loss, rotor copper loss. So, then whatever is going, there will be friction and windage loss, because there is air and there will be, this is rotating, the air gap is very small in millimeters, few millimeters only. If you put it inside, you can see few millimeters. So, there actually there will be lot of friction, viscosity, also because of winding, bearing, etc. there will be windage. Windage means because of wind, friction due to wind, viscous friction, and the friction means it is because of bearing and other things. So, there will be rotational losses. Then finally, the shaft power is available, P out. So, total this is P in and this is P out. So, you can say P out plus losses. P in is equal to P out plus losses. What are the losses? The losses is windage and friction loss, PF, copper loss in the rotor, copper loss in the stator, core loss, etc. So, that becomes the complete efficiency. So, I will stop here. We will go to the next lecture.